Just asking if Eric was well, I think last time I think also, I was going to be I was in Greenland.
Plastic one is that no one is there, they just move, you know. If they get into the momentum, they
Please talk of the moving capacity. We are very hesitant because we will be there first. Much like how the biggest problem is there is no living. People is actually living
Okay, welcome everyone. Looks like the weather is still sort of summery. We haven't yet gotten to the cold time, but we will in a couple of weeks have a team photo, hopefully, assuming the weather will be okay. Today we have, as usual, 4 interesting presentations. First by Yifei Jin. You can see his room number, office number at the CFA, in case you want to speak with him afterwards. His talk is about comprehensive nebular emission-line modeling. And after that, we hear from Emma Esparza-Borges. Is she here?
Yeah.
Okay. And she will tell us about detecting molecules in the atmospheres of WASP-39b, applying standard cross-correlation techniques to JWST data. We very much look forward to that. Eric Koch, an SMA Fellow. Is Eric here? Over here. over there, will tell us about resolving the diffuse interstellar medium across the nearby galaxy population with JWST again. How does feedback shape the diffuse interstellar medium? And then finally, we'll hear from a visitor from New York City, the Flatiron CCA, who we heard at the discussion, the ITC discussion at 11, Chirag Modi, sitting over there. He will tell us what he was discussing at 11, machine learning and astrophysics. The question, at least that's the title that I have. Will you speak about something else?
It is similar, but it's not machine learning and astro.
Well, that's what I was given. In any event, let's put it this way. Is artificial intelligence more useful for astrophysics than natural intelligence? Okay. Yifei, go ahead.
Thank you, Always, and thanks everyone. And after a very long discussion on the pioneer machine learning technique, I would like to talk about some quite old-fashioned multi-color radial transport technique. So I'm talking about the model about the nebular emission line with a kind of comprehensive consideration of the environment. So we know that if we observe a galaxy, we will see the spectral like this, and we have the continuum from the stars, and we have very beautiful emission lines. And there's so much information can be extracted from this emission line. For example, from this emission line, we can get the information of the metallicity of the ISM, the density of the ISM, and temperature of the ISM. Also, from this emission line, by using the line ratios, we can separate different ionizing sources, like the star formation regions, or the agent or shocks. Also, it will give us some information of the property of the ionization fields. However, if you have the spectra like this, how do we get this kind of information from spectra? We cannot just read the spectra and say, okay, we get the parameters. We need some tool. The tool is the photoanalysis code. So what we do here is that you will have a set of input parameters which has some physical meaning, and you put them into the photoionization code, like the cloudy or mapping, which we use nowadays. And the photoionization code will give you a theoretical emission line spectrum. And you will compare the theoretical spectrum with the observed spectrum to find the best fit model. Then you will make a connection between the spectrum and the input parameters. Then you will get some information of the physical parameter. So the photoanalytic code is a bridge to connect these two parts of the science. However, there are two basic shortcuts, shortage of this current photoanalytic code. First is that the current photoanalytic code assumes a kind of simple geometry. In current photoanalytic code, we have two basic geometries. One is the spherical, the other is planetary. You will find this kind of geometries are quite simple. But if you look at the nearby H2 region like the Orion, this is the picture of Orion from JWST, and you will find there are so many structures within the H2 region. And these structures are caused by the turbulence of the ISM or the... Okay, thanks. Caused by the turbulence of the ISM or the stellar winds. So there are some structures which cannot be reproduced by current photoionization code. At high redshift, people find that they measure the velocity dispersion and the ratio between the rotation velocity over the velocity dispersion of the galaxy disk, and they find this parameter changes along cosmic time. They find the V over sigma decline across the cosmic time. That means at high redshift, the gaseous is more like a velocity dispersion dominate. That means the turbulence is dominating the gaseous motion at high redshift. So you can expect that at high redshift, the H2 region should have much more complex structures because the ISM is much more turbulent. Another thing that the current photoanalytic code cannot reproduce is the so-called diffuse ionized gas. This is the image of the nearby spiral galaxies, and the contour, the blue and red contours are the H2 regions. And between these H2 regions, you can still find some gaseous part. That is the diffuse ionized gas. This gas is ionized by either the low mass stars or the leaking ionizing photons leaked from the H2 region. But the current photonic code cannot reproduce this kind of leaked ionizing photons because they don't have this kind of function. So they cannot reproduce the diffuse ionized gas from the first principle. And at high redshift, you can imagine that because the galaxy is far from us, you will see the galaxies will have a very high resolution and change to a very low resolution. And you will see the pixels with the emission as a mixture between the emissions from the H2 region and from the diffuse ionized gas. And another problem is that at high redshift, we need to produce the escape fraction and to establish the relationship between the line ratio and the escape fraction of the ionized photon. But the current photonic code cannot reproduce this kind of relation because the geometry of the H2 region is not that kind of realistic. So we need this kind of model to consider the realistic H2 region geometries or structures. So motivated by this, we developed this new 3D code. We call it Messenger Monte Carlo Mappings 5 or MQ. So this is a new code. It's a Monte Carlo code. Compared to the previous or the 1D code like cloudy or current mappings, it has this kind of features. In this new code, you can set up an arbitrary geometry or any geometry you want. But in the previous one, you can only assume the nebula has a very simple geometry, like the spherical or plane parallel. And also in these new models, you will have, this new code, you will have quite realistic radiative transfer. But in the previous or the 1D code, you can only have very simple assumption of the radiation transfer. And also in this code, you don't need to assume how the nebula is bounded. That means you don't need to assume the nebula ended at some condition. You can let the ionizing photon travel freely in the ISM to see how the nebula is ended. So you don't need to do some arbitrary assumption like the density bounded or the radiation bounded. So this is the new code. This is a feature, and this is why we need these features make this code a kind of promising tool for us to understand the emission lines more realistically. Now with this code, we first to reproduce the diffuse ionized gas. So we set a kind of toy model. This is one slice of the data cube of the density distribution we put in our code. Here you will see three parts of the density distribution. First part is this very high dense cloud. And also you have the intermediate dense clump and a very low dense region, open region. And the right panels, you will see the distribution of the H beta flux. And you will find the very beautiful or very bright bottom of the nebula and a very large open ionizing zone. And here, the green region I highlight here, it indicates the position of the intermediate density clump. And it's very interesting. These two parts you will see, these two parts are behind this clump, and they cannot be ionized by the photons emitted from the star directly. These regions are the so-called diffuse ionized regions or diffuse ionized gas. They are ionized by the photon leaked from the H2 region during the radiation transfer process. So in this code, we successfully reproduce the diffuse ionized gas from the first principle. Another thing is very interesting is that we can produce the turbulent, the nebula in a turbulent ISM and project the H2 region onto a 2D plan to see how this nebula look like if we look them on the sky. So here you see in each panel you see the map of the emission-line ratios, and the left side of each panel is the distribution of the emission-line ratios of the turbulent H2 region, and the right side is the distribution predicted from the 1D code or cloudy or mappings, and you will find the distribution are quite different, and they are quite different. And if you compare the model prediction we give with the observation we have from the signal survey, this is a very high resolution H2 region observation. And you will find that the structure here, you can see the fluctuation of the line ratios is exactly we predicted from our models. So after seeing this kind of result, we are quite happy and confident that our model is quite promising to interpret the emission line behaviors in nowadays I-field data. Another thing is that we can study the internal structures of the H2 region. Here we just see the temperature structure and the electric density structure of the H2 region. So here you see the x-axis is the distance to the center star, and the y-axis here is the temperature, and here is the density. You will find the electric temperature increase along the distance to the star, and the density decreasing along the distance to the star. And if you compare to the observation, the Orion, you will find we see the same trend in Orion, that the temperature increasing and the density decreasing. So this is also very promising result we get, that our code is quite good to reproduce the realistic properties of the H2 region. And what about the integrated emission lines? For example, if you study galaxies, you have a large sample, and for the high redshift one, you don't have the spatial reserved data, you probably will integrate the emission lines from the whole H2 region to do some analysis. How the geometry will affect the integrated emission lines? Here is the result. What we do is that we produce a turbulent H2 region, and we produce a counterpart of this H2 region. So the counterpart one is a 1D, and apart from the geometries, other inputs are the same. So you will see the emission lines changes along between different geometries. And here the y-axis is the ratio between the emission flux predicted from the turbulent model over the flux predicted from the 1D model. And you will find that N2, S2, and O1 will change dramatically with the geometry. That's because these emission lines are located at the boundary of the H2 region. So if you have the turbulent H2 region, the boundary of the H2 region will increase. It will increase the volume of these emission lines. That's why the total flux of these emission lines increase. So I think I should stop here. Now we have this kind of model or code, and with this code at CFA, what we will do is that we will run large H2 region grid. In this grid, we will use different Mach number to describe the turbulent ISM environment, and also we will use some information from the cosmological simulations to give us some hint or sense of the environment, what kind of environment the H2 region should be located. And also we will use the very great stellar population model created here. And also as to the application part, with this code, people can use this code to interpret some turbulent H2 region, especially at high redshift. And also they can describe the emissions created from the H2 region with complex structures like the bubbles in the slot-forming regions. And also with this code, it can be used to interpret the emission lines observed from SDSS-5 local volume vapor. So this is the Orion observed by the local volume mapper, and you will find that there are some structures should be interpreted by this kind of code, which have the spatial reserved information. So my office is here. If you are interested, please talk to me. Thanks.
Obviously, the radiation coming from stars affects the environment, but it's also true that outflows the
Yes.
shape. So that would also change the line transfer significantly. Have you looked into it?
Yeah, that's what we are doing. That's why we say we will have a hydrodynamic simulation here. Yes.
Okay, so that's for the future.
Yes.
Comments, Ramesh?
So this is the Monte Carlo method, you said, right?
Yes.
So do you have a limit on how much optical depth you can handle?
We never think of this.
Okay.
Yeah, we just let it go and to see whether the convergence meets the requirement. If we meet the requirement, we stop the running. Yes. Yeah. We never look into this kind of, but we can look into this later.
Yeah.
Yes.
There must be a limit beyond which
Yes.
it probably will not converge in any reasonable time.
Yes, you're right.
What was the question? Yes, go ahead.
Nice talk. I was wondering if the turbulence makes the line ratios any different, and so if that's a complication for driving
This one?
ionization sources. Yeah.
This one. Why they changes the line ratio?
Does it change the line ratios, or is it?
Yeah, it changes line ratios because the density distribution changes.
And is it the problem like for statistics like the diagrams of derive?
Yes, it is. For all the diagnostics emission lines.
Can you improve it based on your results? Or?
Yes, this is why we need that's why we need the large grid, because with the large grid we can do some systematic study to see how the diagnostic emission lines changes with the geometry. Yes, like the metallicity calibrations and Vp diagrams. Yes.
Do you include dust at all?
In this code, the dust just provide the heating source.
There was a question over there. Go ahead. Is it Morgan or someone asked over there? Oh, okay.
Is non-equilibrium ionization concerned at all?
Non-equivalence?
Yeah.
Yeah, you can always get non-equivalence here. It's included, yes.
So the answer is he doesn't include non-equilibrium.
No, we don't include
Okay,
molecular.
cool.
Yes. This is the only thing we don't include. Yes.
Okay, well, let's thank Yifei again.
Well, hi everyone. I am Esparza-Borges from the Instituto de Astrofísica de Canarias. I am a PhD student there. And today I'm going to talk about our work on detecting molecules in the planet WASP-39b using data from JWST, but more importantly, what is novel here is using standard cross-correlation techniques. So WASP-39b is a hot Jupiter planet with an equilibrium temperature of 1,200 kelvins, and it is orbiting a solar-type star, slightly smaller than the Sun, with an orbital period of 4 days. In this study, we aim to look for carbon monoxide in the atmosphere of this planet. And this is important in the case of giant planets. I mean, carbon monoxide is important in this kind of planets because it is expected to be the dominant carbon-bearing molecule. And also, if we have carbon monoxide measurements and water measurements, we can be able to estimate the carbon-to-oxygen ratios. So WASP-39b was observed with JWST for the first time on summer 2022. And this was performed under the early release science program, and they observed 4 transits of WASP-39b. They used the near-spec instrument, either with the PRISM and the G395H GRISM modes. Also, they used NIRCam instrument and NIRIS. And the very first science results extracted from these observations were already published in Nature. And here, the authors were able to detect several species in the atmosphere of WASP-39b. For example, they detected sodium, water, carbon dioxide. They even detected sulfur dioxide, which was an unexpected photochemical product in the atmosphere. And they were also able to detect carbon monoxide, but only using the near-spec PRISM dataset. However, the authors were not able to detect carbon monoxide using near-spec G395 dataset, which actually has higher spectral resolution. That's why in our study we aimed to look for carbon monoxide using this G395 GRISM dataset, and to do so we reduced the data using Tiberius pipeline, which was developed by James Kirk, and we focused for our cross-correlation analysis only in the NRS2 detector because it is covering the spectral wavelength range of interest for carbon monoxide. And specifically, we decided to perform the cross-correlations only in this tiny portion of the transmission spectrum that goes from 4.6 to 5 microns, because that's where we are expecting the carbon monoxide contribution to be significant over water and carbon dioxide. So, as I have already said, here we aim to do a cross-correlation study. And to perform cross-correlations, we need the data that we already have, but we need to generate a carbon monoxide template in order to perform them. So to generate this carbon monoxide template, we decided to use Petit-Trans, which is a radiative transfer code. And we decided to generate an atmospheric model of an atmosphere from a planet with similar characteristics than WASP-39b, but considering that its atmosphere was composed only by carbon monoxide. We also use the line-by-line radiative transfer mode that is providing the highest possible resolution output with a resolution of 10 to the 6. And we performed several assumptions as the planetary radius, the surface gravity. We also assumed an isothermal profile in the atmosphere. And also we assumed the top and bottom pressure values in the atmosphere. And as an input for Petit-Trans, we used the line lists of carbon monoxide coming from high temp. And we perform our cross-correlation analysis in parallel, either for the carbon monoxide main isotopolog line list that is providing this atmospheric model here that we generated with Petit-Trans, and we also do it for the carbon monoxide all isotopologs line list that is providing this model here. So now we have a high resolution atmospheric model, and the next step we need to do is to lower the resolution of this model in order to match the resolution of our observation. And to do this, we used Spectre's Python module. And then we just need to normalize our model we used in this case a fourth order polynomial, and we subtracted it and we obtained the templates for both carbon monoxide line lists. For those of you that are not very familiar with the cross-correlation technique, when we are performing a cross-correlation, what we are actually doing is to compare a certain data set with a certain template. And we are doing this comparison point by point within a radial velocity range using a certain radial velocity step. So we compare the template with the data in each radial velocity step, and in this way we obtain as output of the cross-correlation function. You can see an example here. So we performed cross-correlations between the portion that we selected of the transmission, of the observed transmission spectrum, where carbon monoxide is expected to be predominant, with the carbon monoxide templates that we generated. And we performed these cross-correlations over a range of plus minus 1,000 kilometers per second, using a step of 6 kilometers per second. And that's how we obtained these results that I am showing here. You can see here the cross-correlation functions that were obtained doing the cross-correlation of the data and our carbon monoxide templates. Here is the result for the main isotopolog line list, and here the result for all isotopologs. And as you can see, in both cases, we are seeing a central peak that is shifted towards approximately minus 80 kilometers per second. And this central peak is surrounded by two secondary peaks that you can see here. And the first time that we did this and we saw these secondary peaks, we didn't know where these peaks were coming from. And we were wondering what was producing these peaks. So in order to answer this question, we decided to perform the self-correlation of the carbon monoxide template. So we cross-correlated the carbon monoxide template with itself. And we obtained the cross-correlation functions that I am showing here as blue shaded regions in the back of both plots. And as you can see, the secondary peaks are also appearing in this self-correlation of carbon monoxide. And what this is telling us is that the fact of the appearance of the secondary peaks in our data to template cross-correlation function is actually reinforcing that the signal that we are seeing is coming from carbon monoxide. And we think that these secondary peaks are produced because of the periodic pattern in the line list, in the distribution of lines in carbon monoxide. And also, I would like you to keep in mind these numbers here, which are the barycentric velocity of WASP-39 system, and also the JWST barycentric velocity at the time of observation. And these numbers are explaining us why our central peak is shifted towards minus 80 kilometers per second. Now let's zoom in the main peak, and we want to measure precisely the radial velocity at which each peak is centered, and also we want to measure the significance of these peaks. And to do so, we performed 30,000 random samples of the transmission spectrum within the observational error bars. And we performed cross correlations in each of these samples, and we fitted a Gaussian to the central peak for each case. And that's how we're measuring where the peaks are centered and the significance. And as a result, we obtained that the radial velocity at which the peaks are centered is consistent with each other, and also it is consistent with the expected systemic velocity relative to JWST at the time of the observations. And also another important result that we are getting here is that the significance is slightly increasing when we are taking into account all isotopologues in the line list. I know this increase is very slight, but this might be suggesting that in the future we could be able to distinguish isotopologues. So these are the messages that I would like you to bring home. First, we were able to detect carbon monoxide, to confirm the detection of carbon monoxide in G395 dataset using standard cross-correlation techniques. Here we are using a dataset that has a resolution of around 3,600, and the cross-correlations are working here. Also, we think that the secondary peaks in the cross-correlation function could be exploited in the future in order to increase the confidence of future detections in exoplanet atmospheres. And the fact that the significance of the detection is increasing when we are including all isotopologues is suggesting us that in the future we might be able to perform individual isotopologue searches. So thank you very much for your attention. I am leaving here my contact information. Also, this QR code here will link you directly to the article that we just published in the Astrophysical Journal Letters. And thanks again.
So the speed, obviously JWST is at L2, the Lagrange point 2, so the speed that it moves relative to the source changes over the systems, right?
Yes.
So that could be used to test, right, whether you get a good fit.
Exactly. Actually, that is giving us an extra confidence that the carbon monoxide signal that we are detecting is coming from the system and from the planet. If we were obtaining these central peaks in another velocity, they might not be coming from there.
Go ahead, Eric.
So you measured a bunch of different molecules, and you gave a talk about CO. Is there something interesting about CO in particular? Or?
Well, this was our first study with cross-correlation. So carbon monoxide is the first molecule that we used to test this technique. Currently, we are also looking for other molecules, but this was our very first study.
Yes, go ahead.
Yeah, so this is awesome. So now that you see that you can detect this using the cross-correlation, you have a better idea of why it was missed in the retrieval and like what's going wrong with the retrievals that they can't see this?
Yeah, we're trying to understand it better. Actually, we're currently, we have a collaboration ongoing with some retrieval experts to just find out why it didn't work with this certain data set with the retrievals and it is working with the cross-correlation function. Actually, in the initial analysis of the retrievals, they saw a hint of carbon monoxide, but they were not able to confidently detect it.
Any other comments, questions? If not, let's thank Emma again.
Great. My name's Koch, and I'm excited to share some of our recent results, the early results from the PHANGS-JWST program. And I'm going to focus on one small part of our large set of papers and talk about something that we didn't actually think ahead of time that we'd be able to use this data for, and that's to actually map the structure of the ISM in more diffuse components. And so along with myself, let's point out that this work also includes two other people here at the CFA, Jakob Denbrock and Sarah Jefferson. All right. So about, I guess, 14 months ago or so, we started getting pictures like this out of JWST, and I think it looked pretty incredible, maybe to the point that we're starting to just expect these types of images. But the first time I was asked by this, about this picture from someone outside the team, they didn't think it was real. They thought it was a simulation. So I think that says something good about galaxy scale simulations. And we'll come back to that right at the end. All right. So what did we have before? We had this, what is still an incredible view with Spitzer. Spitzer is incredibly important because it can fill a massive field of view. So it really tells us where we want to point JWST's much smaller field of view to look at interesting areas in these nearby galaxies. And so the place that we started looking first was the center of these galaxies. And so we went from a picture like this, the whole wide field view that Spitzer was able to achieve, and started getting details like this. And so this is one of the bands that we saw in the previous image, but now really just focusing and highlighting just how much structure and richness there is in this data set. Okay, so what are we doing with these data? They are part of this larger program called PHANGS. It's the Physics at High Angular Resolution in Nearby Galaxies. It is a combination of different large programs on ALMA to map the cold gas, MUSE, optical IFU, as well as Hubble. And so we were very fortunate to be awarded one of the JWST Cycle 1 Treasury programs, and actually have an ongoing Cycle 2 Treasury program as well. That will be 55 more galaxies. I'm just talking about the first 4 here. So the goal of PHANGS is to get a high-resolution view across the multi-wavelength spectrum, but actually sample the nearby galaxy population such that we're covering the star-forming main sequence of the redshift 0 universe. And so the idea here is to get these large samples to understand how the star formation life cycle varies, but be able to connect that to the larger questions of galaxy evolution and the population of galaxies as a whole. So our sample is primarily in the south. This is because we're using ALMA and the VLT, but it samples the parameter space fairly well. The first set, and what we got in Cycle 1, which is now completed, we have all 19 galaxies. They were specifically the ones where we have overlapping in all the other different instruments so that we can create this very rich multi-wavelength data set. And so what JWST adds to the previous data is really the ability to go after this very embedded young massive star formation, as well as different properties of the dust in these galaxies. And so the team really came together last fall. We published 21 letters in the special edition in AppJ Letters. And it really was a team effort with about 70 or 80 people constantly engaged over multiple months. It was a lot of fun. I am not going to cover all 21 letters, you might be happy to know. But they cover the whole range of what we thought we'd be able to do with JWST, starting with just these 4 galaxies that happen to be observed first. So this includes embedded star formation, the timescales of star formation, the impact of stellar feedback, and then the 2 parts that I will talk a little bit more about here. What can we use from dust physics to better understand the structure of the ISM with these new data? These are Hubble bands, so they're effectively real colors. Yeah. All right, and so the secret to this is really what can we get in the mid-infrared. I'm going to highlight what we're understanding from polycyclic aromatic hydrocarbons, or PAHs. These are small dust grains, and so what we see in the mid-infrared, these are the 4 bands of the MIRI instrument that we observed in. We have 2 bands that, and this is a representative spectrum of the near and mid-infrared from dust models. So we get a combination of bands tracing the warm dust, its black body-like emission, in 2 bands. And then we have these vibrational structures that come from the PAHs at about 7.7 microns and 11.3. And it's the combination of all 4 of those bands that ends up giving us the picture that we see here. And so this is telling us about both the warm dust and these small dust grains. Right, so it's tracing both components of this. And so why do we care about this for the ISM structure? Well, if you remember back to how the photodissociation region works, in particular with how we understand how molecular hydrogen forms in the nearby universe. We have far ultraviolet radiation, and we have these layers as you get into the molecular cloud or the star-forming gas. And the most important part here is that we really think that it's the dust that provides most of the shielding from that ultraviolet radiation. So you have a high enough column that you can start to get molecular hydrogen as well as carbon monoxide, which is the way that we typically trace the cold molecular gas in these galaxies. But the dust is crucially mixed in with both of these different phases. So what we did was we started to compare the properties that we see of the molecular gas to different things in the mid-infrared. And this is actually a compilation of literature data. So this is on still galaxy scales, taking existing data from Spitzer and WISE and updating it with new maps that we have, mostly from ALMA, of the carbon monoxide. And so what you're seeing here on the y-axis is the brightness in the carbon monoxide, so that's tracing the molecular gas. The x-axis is the brightness in the mid-infrared, and there's a very good correlation. And what we find, though, for the bands that primarily trace the PAH features, that slope is a little bit shallower. And so that's suggesting that it's picking up on a component that the molecular gas, or the CO, is not directly tracing, perhaps this sort of more diffuse atomic component. So what we did with the JWST data is actually get a spatially resolved view of what this empirical correlation is telling us. So here I have the molecular gas, I have the H alpha, so showing where the H2 regions are. If you look carefully, I'm going to switch this now to two bands that we see in the infrared. And so we have one band primarily tracing the PAHs at about 7 microns, another tracing the warm dust at about 21 microns. And what we end up finding is that the structure is very similar, but the PAHs are far more similar to the molecular gas. The warm dust tends to trace the H2 regions a bit better, and that's because PAHs are being destroyed in those H2 regions, but the warm dust, the larger dust grain, are just being heated and re-emitting that emission. And so if there's this strong correlation between these different parts, it suggests that if we have some way with these correlations to go from a brightness of the PAHs to predict the brightness of CO, then we can use our other favorite conversion, the XCO factor or alpha CO, to go from a predicted CO to a total gas surface density. Now, there's a lot of problems in this, and there's a lot of systematics that I'm hiding. We think that this works fairly well because it's pretty close to Milky Way-like conditions in most of our sources, so it's close to how we've calibrated most of these parameters in the first place. So that's the idea. Can we take a PAH band and convert it into a total gas surface density? And so this is what we tried to do, some work that Karen Sandstrom and I led. So this is taking our maps of one of the PAH bands and just scaling it to an effective gas surface density. And the important part here is that because it's Milky Way-like conditions, at about 10 solar masses per parsec squared, that surface density, is where we expect the medium to change from mostly molecular clouds or molecular dominated into the atomic phase. And so that's what this black contour is here. And what I want you to look at is how much structure is still picked up by JWST below that threshold. And so what this really means is that with PAHs, we're tracing the atomic medium on scales that we've never had access before with a sensitivity we've also never had access for. So that's the main reason why this is so exciting. We simply can't do this with other tracers of the atomic ISM, such as the 21 centimeter line. We can't get the same sensitivity, and we can't get the same resolution. And so one thing that we started to look at just within this early work is different measures of the topology. If this is actually giving us the total gas surface density, it's tracing different components of the molecular and the atomic component. And so we tried one thing called the genus statistic. This is a variation from the version that's used in cosmology. The idea is that at a given threshold, we look at how many sources are above that threshold. So if it's positive, it's more meatball-like. If it's negative, it's more Swiss cheese-like, so source versus hole dominated. And what was interesting is that we see this 10 solar mass per parsec squared transition happen roughly where we're seeing the change in topology, at least for 3 of the sources. So that's potentially interesting. It's telling us that there's a morphological difference in potentially the molecular versus the atomic phase. Now this doesn't work very well for this other galaxy. That's because it's at a lower metallicity. It's a dwarf spiral galaxy instead of more of a Milky Way-like. And this is really saying that this correlation that we've used to do the scaling is just not holding. We need to be able to change it or map that out better to different galactic environments. And so one interesting thing, if we're actually tracing the atomic ISM on these scales, well, you can imagine starting to directly compare this to the column densities predicted in galaxy scale simulations. And so we did this with just a couple snapshots. The snapshots themselves are not important. The idea was just, can we take an actual gas surface density, compare it to what we're seeing now with JWST? Kind of looks similar for some things. We need to do a little bit more and understand this connection a little bit better, potentially use different statistics. But that leads me just into the question that I want to leave you with. And that is, if we're now getting the actual structure of the atomic ISM on these scales that we haven't had before, it really adds an extra constraint for these galaxy scale simulations. And we can ask, does the stellar feedback prescription that you're using also predict the structure of the atomic ISM, not just the star formation rate or the content of the molecular gas? And so we think that we can start doing this with JWST using the PAH mission. I showed a few galaxies up here. We have 15 more, 55 more on the way over the next year or so. So we actually have a pretty big observational space where we can now start to do real meaningful comparisons to similar gas surface density maps of galaxy scale simulations. So, thank you.
So Eric, obviously what we're looking at the projection, right? So
Yeah.
do you worry about the third dimension that we're missing in sort of smoothing or introducing? I mean, because you're talking about fine structure, of course, and it could vary with scale.
Right. So something that we tried here that I'm not directly showing is we were putting the simulations in effectively the same observed frame. So inclined to the similar effect, smooth to a similar resolution. At least for the couple that we looked at, it didn't seem to be much of an effect, at least for this one statistic that we started to look at. But we did try to match them best as we could.
Okay, Eric again.
So I thought we used to think that the H2 and the CO were self-shielding. And now you're saying that it's the dust is more important than that. It's interesting. 25 years ago, there was a paper by Drain and Bertoldi, and they did this detailed analysis of 1,000 H2 absorption lines, and they came up with this incredibly simple answer. They said it's proportional to the column density in some sense, right? And so that paper has over 1,000 citations because everybody loves this. They know this thing. We don't have to worry about this. And so now you're saying they got the right answer from a completely incorrect analysis. Is that?
I maybe wouldn't say that quite as strongly. I haven't directly worked on that, but I know that there's, within the last 10 years or so, there's a series of papers that are looking at the impact of dust versus H2 shielding. My understanding is that the H2 shielding is more important when you're at solar or supersolar metallicity, but the dust can be more important at slightly subsolar metallicities.
That's interesting.
Juliana?
Also a question on the dust. So you're relying on absorption and re-emission to do this measurement, right? Is it possible that that emission could tell you anything about the size distribution of the dust? And is it possible that that size distribution would affect the shielding that you observe? The concentrations?
I think it would. So right now we're not looking at that in as much depth. We're really doing a couple empirical correlations and taking a single band, but we do have imaging across 8 different bands where we can try to start to separate out the PAHs versus the larger dust grain and the warm dust component. Practically speaking, I think we need to go back with spectroscopy with JWST to do this in a little bit more of a detailed fashion. It's definitely showing us, for example, at 10 micron, we expected it to mostly just be black body like warm dust. There's more contamination from PAHs than we expected. So some of the simple assumptions definitely start to break down at some point.
Do you see like dependence on the pH with metallicity? Because I think like that assumption of the conversion is like assuming pH is constant with metallicity.
these are pretty much only solar metallicity, so we don't have much of a range to test that. This is our lowest metallicity galaxy. It's about a half solar. And this scaling, I wouldn't trust this gas surface density for this one. Something is definitely off, and I think that's where this is coming in, and we do need to make some adjustment for that. And we do have a few of our cycle 2 targets. We'll cover a slightly larger range in metallicity, and maybe we can try to correct for that there.
Okay, if there are no more questions, let's thank again.
Hi. So I'm Chirag. I'm a postdoc at Flatiron Institute, and I'd like to talk about hybrid SBI, or this. Okay. Right. So this is going to be qualitatively different from the other talks that we have seen and things. So. Briefly, this was work done with Oliver Philcox at Flatiron, and the goal here is to combine how we have been doing cosmology analysis using perturbation theory so far with how some people have been trying to do it for the next generation of surveys using simulation-based inference, and why we should think about combining the two and how you do it correctly. Okay, so the outline will be briefly this. I would first very briefly introduce what simulations-based inference is and why do we care about that. Second, why we should start thinking about something like hybrid simulation-based inference, and I will present a proof of principle of the technique and like what we need to do next to actually do it for upcoming surveys in a sense. Okay. So until now, in cosmology, most of the analysis has been done using analytic tools based on perturbation theory or EFT of LSS, where you write down some analytic equations, analytic models like this. You assume a Gaussian likelihood for your data, and you mostly focus on low-dimensional summary statistics like power spectrum and bispectrum. The challenge, and this has been quite successful for quasi-linear and quasi-linear scales, or the large scales that we have. But going ahead, I think all the cosmologists kind of agree that we would like to go beyond just using 2 and 3 point correlation functions, and we would like to push to smaller scales. So we don't want to just work on the large scales or quasi-linear scales as we have so far. People have come with a lot of summary statistics like peak counts, marked power spectrum, wavelet coefficients, k nearest neighbor. Every cosmology group has their own favorite statistic at this point. Some people want to use ML-based summary statistics, which are supposed to be optimal in this setting. The challenge is that for all of these, we will need to come up with theoretical models or analytic models the way we came for perturbation for power spectrum and bispectrum. You need to verify what their likelihood distribution looks like. Pushing to smaller scales with perturbation theory is not really possible because by its definition it breaks down in nonlinear regimes and stuff, and including service systematics for all of these is also non-trivial. So there is kind of a growing understanding in the community that we would, if we can, doing most of these things computationally using simulations is much easier than to do them analytically in this sense. So in that sense, people would want to use simulations for this if possible. So that's kind of where simulation-based inference enters. It also goes under the name of likelihood for inference or implicit inference. And the main observation which motivates this is the fact that even if you do not know what your distribution of the statistic or the data that you want to model looks like, by the fact that you are able to generate simulations, you essentially generate samples from this joint distribution of your underlying parameters and the data in this case. So what people do, what you can do after this is that if I take my prior space, if I sample parameters, if I generate simulations at those parameters and calculate the data statistic from all of them, you can then either try to learn using any flexible parametric model like normalizing flows, you can either try to learn the likelihood distribution of your data, or you can directly learn the posterior distribution of the data in this sense. You can show statistically this is correct, and the only part where machine learning is entering in here is like you're using normalizing flow, but otherwise you can do this, you can prove statistically that these things are in the limit of a large number of simulations, you get the correct answer from this back. And people have done it as a proof of principle. People have tried to apply this on data. So this is just one of the works that I'm showing from Simbic collaboration, which was headed by Chang Hu-Ha at Princeton. And what they did was they took the 100,000 galaxies from Bose South Galactic Cap. They used Quixote simulations that were generated at Flatiron to train their inference procedure. And using these two, they were able to go to different statistics like CNN field level statistics and wavelet statistics, and they were able to push to smaller scales up to K of 0.5 with power spectrum and bispectrum. So what I'm showing here is on the dashed lines are the contours from what perturbation theory analysis has given us so far, and the different colored contours are the different statistics from the SBI approach. And you can kind of see that like if you push to smaller scales, or if you can use higher order statistics, you do get more information out. So it leads to better constraints across the board for these things. So the question we wanted to ask, like, okay, have we solved this problem? Can we now use any statistic going ahead in the case? And to see that, like what we, in the future, what we'll have is surveys like DESI or LSST, which will require much larger, which probe much larger volume in the universe, and which will probably require much high resolution simulation, because you'll be probing galaxies which are much fainter than we have before. Your data will get much better in quality, so your simulations should also correspond to that high quality data, and so you'll probably need more accurate forward models in this case. Now, if you want to generate training data set for that, if you look at the current computational landscape, so Quixote Latin Hypercube is probably the largest simulation suite that we have for training these kind of procedures. It required 10 million CPU hours, but it is only 1 gigaparsec in volume, and that is smaller than the Bose survey, which ended in 2016. And that is why in the previous slide, Simbic collaboration only used the South Galactic Cap of the survey rather than using the full survey in this case. It is also 1 megaparsec in resolution, which I would say is not high resolution enough to probe the galaxies that we'll have in the future. So the understanding is probably that it is computationally prohibitive to scale these kind of approaches for the next generation of surveys, especially if you want to use more accurate galaxy models. And so the question we wanted to ask, like, how do we scale for the future? So to do that, let's go back to the motivation. We wanted to use simulations-based inference to go to smaller scales and use higher order statistics, right? With the understanding that in these regimes, you cannot model things analytically. But on the larger scales, this is probably not necessary, because we know that on the larger scales, the density field and the observables are Gaussian. We have been using perturbation theory successfully for those things. There have been recent papers which kind of show that, like, just using power spectrum and bispectrum on these scales, the way we have been doing so far, is probably close to optimal already in this case. So if we use any higher order statistic, we'll probably not gain as much as we want to, as we can. So the motivation for hybrid simulation-based inference is to combine perturbation theory on large scales with simulations-based inference only on the small scales. And to see how we can do that is assume that you have a data vector x, which can be split into two components like xl and xs, which is like large scale component and a small scale component. Then the likelihood of that data vector can be correctly decomposed into these two parts, where you have a large scale likelihood and a small scale likelihood, which is now conditioned on the parameters and the large scale data vector that you are seeing in this case. So the goal here is then to take the large scale data vector to be the power spectrum or the bispectrum that we are doing so far. The model for that will be given by perturbation theory, and we know the likelihood function is Gaussian to a good degree there. The small scale component can be now anything. It can be power spectrum, bispectrum, or the higher order statistic. And this is the component that you want to learn using the simulation-based inference only. The goal here is that because these are small scale components, you should be able to learn them by running only small sub-volume simulations instead of simulating the whole survey volume at high fidelity in this case. But of course, there are no free lunches, so there are two new issues here. The first is that in the way that you have written down that likelihood term, where the small scale is now conditioned on the large scale data vector as well, you cannot just run a small volume simulation independently. You need to somehow, if you are running a small volume simulation, you need to also figure out in what is the large scale data vector in the universe in which this small scale simulation is coming from. So you need to develop these customized simulations where you run a low fidelity, like say a particle mesh simulation on the full large scale survey volume to calculate the large scale data vector. And then from that particular universe, you take a small sub volume that you do simulations for higher fidelity. To imagine like how this goes is like, think of it as zoom in simulations that you're doing for cosmology at this point in this case. The second challenge will be that you have super sample effects in that if you're only simulating a small volume, in that case the statistic that you'll be measuring will be noisy. A, because you just have less number of modes, and also the small sub volume will be affected by the modes which are large scales and coming from outside the volume. So in the first paper, we just wanted to see about the second, like if you just simulate one sub volume, how much signal do you lose in this case? So what we ended up doing is try to constrain omega matter and sigma 8 from a 3-dimensional dark matter density field using Kyoto simulations. So what we did was the large scale component we took was power spectrum. The small scale statistic that we took was power spectrum on small scales, as well as the wavelet coefficients. To train the simulations-based inference technique, we just took a Kyoto simulation box, chopped it up into 8 small sub-volumes, and used only these sub-volumes for training our simulator in this case. And these are kind of the results. So in the blue, you see what you get from using just perturbation theory on the large scales. In the green and the purple are the two schemes that you use if you use the hybrid simulations-based inference. You are able to gain much better in this case. In the orange is what you would gain if you do the full scale simulation. If you could run a full simulation and just use the simulation based inference in the whole thing, that is slightly better than what hybrid simulation based inference gives, and that is primarily because you have some effective parameters in perturbation theory that you still need to marginalize over in this case. But this is kind of the money plot in that sense. Like, so here what I'm showing in 4 different colors is what happens if I'm training my simulations only using 1 sub-volume versus 2 versus 4 versus 8 sub-volumes in this case. And you see that the constraints kind of get worse as you go from like 8 to 1 sub-volume. But even using just 1/8 of the volume, just using 1 sub-volume, you're still outperforming the traditional analysis by a lot in this case. The point here being that the thing that we were worried about adding noise with the cosmic variance and supersample variance, doesn't really kill the constraints in this case. So that was the main idea, that in hybrid SBI, what we are trying to do is combine perturbation theory on the large scales with simulations-based inference on the small scale, trained using only small sub-volumes. And we think that this is the only realistic path for scaling SBI, at least in the near future, for large sub-volumes. This was a proof of principle work, but these are the 3 steps that we have identified which need to be done for applying it on the surveys. The first is developing these kind of customized simulations. There are tools and techniques out there which do this. For example, you can have zoom-in simulations, or you have these techniques like Escola, which separate the large and small scale evolution explicitly. For galaxies, PT and SBI use different nuisance parameters, but they are not necessarily independent. So you want to model those nuisance parameters simultaneously. This work is actually being led by Gemma, who is here. And then thirdly, you want to account for correct systematic effects, survey systematics and survey masks, which couple large and small scales correctly in this framework. But yeah, this thing. Thanks.
Thank you, Chirag. Just a correction. There is free lunch. You just attended it.
Awesome.
Any other comments? It looks like everything was clear, so let's thank all the speakers again.
More on the engineering What is that? Yeah, so these